Today we're on page 6 of the Chapter 13 AP Chemistry Notes. We're going to be talking about LeChatelier's principle, which says that if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. In order to understand this, let's go back to our story of the barbecue at your house. So remember that you have one of these cool revolving doors. Let's say it's a sunny day, and you have some people coming over to your house. Remember, and I'm going to do this, shorthand here, not with the whole diagram. So let's suppose that 3 people show up at your house outside, and remember that your sunny day ratio is 2 out to 1 in. Let me just fix this. It wasn't really responding to me very well here. So 2 out to 1 in. You realize that what's going to happen is that one of these people has to go in the house. Okay? So at the moment that the 3 people arrived, you were not having an equilibrium situation because you did not have your special 2 to 1 ratio of out to in. So the equilibrium had to shift, or I should say the system had to shift to the left so that one person came in. So in other words, one person was coming in and nobody was going out. But right now, what's going to happen is this person is going to come in the house and this person is going to go out of the house. And so it's going to be at equilibrium. Okay? So the next situation is 3 people show up, but they come up through the basement. Okay? So you have 3 people come in. Now you're, again, not at your special ratio. You're not at your 2 to 1 of out to in. So what has to happen is we have to shift to the right. We have too many people in the house. So when we shift to the right, this person and this person walk outside. And at that moment, nobody was walking in. There was nobody walking in. There was only people walking out. So that means we're shifting to the right. We're reacting more towards the right. But once we have our special ratio of 2 to 1 of out to in, then one of these people is going to walk in and one of these people is going to walk out. And now we're at equilibrium. Okay, so that's what happens, let's say, if you add more people. Let's suppose that we take away people. So let's suppose that some people go home. So we'll just erase this person quickly. It's not erasing very quickly. Okay, we'll just cross them out. So let's suppose that 3 people go home. 1, 2, 3. 3 people go home. So now again, we're not at our special 2 to 1 ratio. So what has to happen is one of these people has to walk out. So we're going to shift to the right. So when we shift to the right, this person, I'll do it in black here, this person is going to walk outside, and now we are at our special ratio of 2 out to 1 in. Okay, so what happens is you shift in a way to compensate for whatever change happens in the equilibrium. All right, there's a little quote that you could write down. This is actually from Mrs. Hofer, who has now retired, but this is what she used to say. She used to say, and this is going to take a little while to write here because it's not really listening. What's with it does the opposite. What's with it does the opposite. What's not with it you can make this out. What's not with it does the same. We'll take some examples in a moment. Okay, so let's move this up here. And, all right, what a mess. We're going to see how this works, okay? So we're going to continue on and go through some examples. Just bear with me here with this video. It's freezing some of the drawings, so we just have to do our best here. Okay, so let's take a look at this equilibrium and see what happens. Here's an equilibrium, and we have nitrogen and 3 hydrogens with 2 ammonias at equilibrium. It's exothermic because the heat is on the right side, and the Kc is 3.810 to the 4th, which is a fairly large number, so it tells you this equilibrium does favor the products at equilibrium. Okay, so let's suppose this is all in one big vessel, and inside this vessel you increase the nitrogen. So you have too much nitrogen. So if you have too much nitrogen, you're increasing the nitrogen. This is what you're doing, and I'm going to put it in parentheses to show that this is what we did. Okay, so this would be like too many people in the house. Too many people in the house. So what are we going to do? We're going to shift to the right to make some people go outside. So we're going to shift to the right. So if people go outside, what's going to happen to the number of umbrellas in the house? The number of umbrellas is going to go down, and the number of people outside is going to go up. So the H2 goes down, and the number of people outside goes up. Excuse me. And the equilibrium constant will stay the same because there's only one thing that changes the constant, and that's temperature. Okay. Now, if you're going to apply the little phrase that we said from Mrs. Hofer, which I'll try to show you again, then what's with it does the opposite. Okay? So here's the thing we changed. We changed this. We made this go up. So what's with it does the opposite. This thing is going to go down. And then what's not with it does the same. I mean, the other side of the equation is going to go up. All right, so let's try the next one. Let's suppose we increase the hydrogen. So now we are going to increase the hydrogen. That's kind of like saying there's way too many umbrellas in the house. So you made lots of umbrellas in the house, and now you're saying, look, we got to get some of these umbrellas outside. So someone has to pick up an umbrella and walk out. So that means the number of people is going to decrease inside the house, and the number of people outside is going to increase. So this goes down, and this goes up because we still shifted to the right, and the equilibrium constant is still the same. And if we do our little saying, what's with it does the opposite. So we made this go up. What's with it does the opposite, goes down. And what's not with it does the same. This goes up. Next one, we're going to increase the ammonia, which are the products. This is what we are changing. So it's like too many people outside the house. Some have to go in, which makes the people inside go up and the umbrellas go up. So this goes up and this goes up. Again, follows the saying of what's with it does the opposite. Nothing's with it. This went up. What's not with it does the same. This goes up. This goes up. Just remember that this equilibrium shift went to the left. Okay, so we'll keep going now in the same process, decreasing N2. So now we're going to make this go down. Again, this is like people leaving the house from the inside. So a lot of people from the inside your house leave. Okay, so that means some people have to walk in the house. When they walk in the house, you have more people coming in and more umbrellas. So this is going to go down and this is going to go up. Okay, this already went down because a lot of people left. So even though you're going to make more people come in the house, overall there's going to be less people than there were before. But the umbrellas will go up and the people outside will go down. You're still going to keep your same ratios, of course, and this time we shifted to the left to make more nitrogen. Okay, we're going to keep going here, and we're going to look at decreasing the hydrogen. So we decrease the hydrogen. It's like taking away all the umbrellas from your house, so we have to shift left so more umbrellas come in, and by doing that, more people are in the house and less people are outside the house. You're going to have an equal ratio. Now, my analogy is not perfect with the umbrellas and the people because when I gave you your 2-to-1 ratio here, I really was only counting the people in and out, okay, out to in. I wasn't even counting the umbrellas. So the math of my analogy is not going to be perfect, okay, but the concept is really what I wanted you to get. Okay, let's go to NH3. NH3 is the product. I'm going to take some of that away. Again, like people outside the house going home, so people have to walk outside the house. That means less people in the house, less umbrellas, and the ratio will stay the same overall for the K. Okay, now we're going to talk about temperature. all of a sudden we have to understand that temperature is going to change the ratio. Okay, so temperature changes the K. So what we're going to do is we're going to increase temperature. So temperature is related to heat. Okay, that's like increasing this. Since heat is a product right here, it's something outside. So in the analogy, let's suppose that at your house you have a big picnic table in your backyard and it is loaded with money. Okay, so every time somebody walks outside with an umbrella, they put down $92 on your table. But every time somebody walks in the house, they pick up $92 to walk in. So now the question is, we increase temperature, all of a sudden there's a big pile of money outside and there's too much money on the table, so we have to bring some of the money in. When we bring some of the money in, we're going to change the ratio. We're going to have less products and more reactants. So that's actually going to make the ratio decrease. Because remember, in this case, because it's exothermic, that K is a ratio of products to reactants. Since K is a ratio of products to reactants, and you are decreasing the products and increasing the reactants, you are decreasing K. So we're going to shift to the left in this case, which makes this go up like people in the house. This goes up like the umbrellas. This goes down like the people outside. Okay, the contrast is over here, and let's just take a look at the bottom of the page because it's hard to read the top right now. So here we go. Again, oops, here's the heat. Pile of money. So now this time we decrease the temperature, which means that some of the money is used to buy some pizza, let's say, and so there's not enough money on the table outside. We need more money outside. So to get more money, we got to get people to walk out of the house and put $92 on the table. So if that happens, then we're going to shift to the right. Less people inside the house, which means less umbrellas. More people in the house, outside the house. I hope I said that right. Less people in, less umbrellas, more people out, and the ratio now is going to go up because, as we said, K is a ratio of products to reactants. So if there are more products and less reactants, this is really frustrating here, this is going to go up, so the K goes up. All right, so far so good. Now we're going to talk about pressure and volume, and pressure and volume have to do with gases. Okay, they're all about gas. So when you get to a question that talks about volume, you're going to need to understand that this has to do with moles of gas. Moles of gas. Okay, so how many moles of gas are on the left side of the equation? We have 4. 4 moles of gas. And look at the right side, we have 2 moles of gas. So if we decrease the volume, that means we have less space. Less space, we want less moles of gas. So we need less gas. So look at the equation. The side with less gas is the right side. So we're going to have to move to the right in this case, which makes this go down, this go down, this go up. And I know that you're going to think that mathematically the K is going to change, but it doesn't, and here's why. Because when you change the volume, you're actually going to change the molarities as well. And by making the volume smaller, all the molarities are going to go up. And so even though these are all changing, the ratio will come out to be the same thing. So just remember that the only thing that changes K is temperature. Okay, next go to the next one. If you're going to talk about more volume, that means you want to make more gas, give it more space. So when you look at the equilibrium, you'll see that there is more gas on the left side because there's 4 moles here and 2 moles here. So that means we're going to shift to the left. So when we shift to the left, that's going to make more of this, more of this, less of this, and an equal amount of K. Still the same. Okay, the last two are trick questions, so we're just going to fly through those real quick. You see that there's no neon in this whole equation. So if there's no neon, everything is going to remain the same. And if you add a catalyst, it just makes things faster, but everything will still remain the same. So the analogy for the catalyst is, in your house, let's say that your door was on a big staircase. So it took people a long time to go up and down the stairs. But then you decided that was too much work for your guests, so you decided to make a tunnel through here. And now the guests could move back and forth easily between the in and the out of the house. And so more people could go back and forth easily, but it still wouldn't change any ratios. It would just make everything faster back and forth than slower over the stairs. Okay, so that's what a catalyst does. It speeds it up, but doesn't change the ratio. And that is Le Chatelier's principle.